Okay, so this will be the second of three videos on matrix multiplication for Math 1410, Spring 2017 semester. So in the previous video, we looked at a number of special cases, and now we want to extend to the general picture. So the cases that we looked at on the last video, we said, okay, if I want to do a row times a column, so if I have, so if my R looks like, say, A1, A2, down to AN, and I have a C which looks like maybe B1, B2 down to BN. And the key thing here is that the number of entries in my row matches the number of entries in my column. So each number in the row R has a partner in the column C. I can pair them all up, and I pair them up using essentially this dot product process, right? So if I want to do R times C, I do A1 times B1, I do A2 times B2, and I continue all the way down to AN times BN, right? So each number from the row on the left can be paired with the corresponding number from the column on the right. We multiply those guys together, and then we sum all of those products. That gives us row times column. If I wanted to do a matrix times a column, right? If I wanted to do so if A is my matrix and X is my column vector, so X here looks like maybe X1 down to Xn. What I do is I say, you know what, I can think of that matrix A as being composed of several rows. Row 1, row 2, down to say row M, multiplied by X. So each one of these rows here, maybe row I, is going to look like AI1, AI2, down to AIN, right? And again, the N here matches the N there. And so I can do each of these row times column products, and I simply do row 1 times X, row 2 times X, all the way down to row M times X. Okay, and similarly we can do a row times a matrix. If I have Y, maybe Y looks like Y1 down to YM. Okay, and I want to do Y times B. So I think of B as being composed of columns. Column 1, column 2, down to, oh, not down. Columns go across. Let's fix that. Column 1, column 2, down to column, let's say N. And I do the row times the first column, so Y times C1. I do Y times the second column, and so on down to Y times the last column, right? Where each one of these columns looks like A1I down to AMI. And again, the M matches with the M. The number of entries are the same. Okay, so we want to put these together now. We want to say, okay, well, if I want to do a general matrix, if I want to form a product A times B, I will think of the matrix A as being composed of rows, I will think of the matrix B as being composed of columns, and I will do each row from A multiplied by each column from B. Okay, so if I want to do AB, right? So I want to do A times B, right? And if A is going to be, let's say, an M by N matrix, and B is going to be, well, for now, let's say it's maybe it's a K by L matrix, okay? K by L. Okay, so I want to do this kind of row times column thing, so I want to think of A as consisting of several rows. Row 1, row 2, down to, well, row M. Okay. I want to think of B as consisting of several columns. Column 1, column 2, down to column L. Okay, and now what do I know? I know that row I from A is going to look like AI1, AI2, down to AIN. I know that column, let's say J, is going to look like B1J, B2J, down to BKJ, right? Where this N matches with that N, and this K matches with this K, right? And I want to form this product. I want to form, in order to form these products, row I times Cj, what do I need? I need the number of entries in my row to match up with the number of entries in my column so that every one of these A's has a corresponding B that it can multiply by. And that means I need N to equal K. Okay? So these guys here, these guys must match. Alright? Once I know that they match, I can form my product. So how do I do this product? I do the first row times the first column, and that's my first entry in the new matrix. I do the first row times the second column, and that's the next entry, and so on all the way down to the let me move things over a little bit so we can fit. So row 1, column 1, row 1, column 2, down to row 1 times the last column, column L. Then I would do the second row times each of the columns, so row 2, column 1, row 2, column 2, down to row 2, column L, and so on down to row M times column 1, row M, column 2, row M, column L. And that's my matrix product. And notice that the result here is an M by L matrix. Okay, so those numbers, that M and that L on the outside, they tell me the size of the product that results from multiplying those two matrices. So that's the general procedure. If I want to do a matrix A times a matrix B, the first thing I have to check is, can I even multiply them? And the way I check is I check those two inside numbers and I see if they match. If they do, I know that the product is defined. I know that the size of the product is given by the M and the L, the numbers on the outside, and then I work out each of the dot products, each of these row times column dot products, right? So a general entry here is going to look like row I times column J. Okay, so here are some examples. We want to form some matrices. So first of all, let's note the sizes. Okay, so A has 2 rows, 3 columns. B has 2 rows, 2 columns. C has 3 rows, 2 columns. So which of these can I form? I can't do A times B because the 3 here does not match the 2 there. Those two numbers are not the same. So A times B is not defined. What about B times A? So this would be, I would be doing a 2 by 2 matrix times a 2 by 3 matrix. That works. Okay, 2 and 2. Those ones are defined. A times C. A is 2 by 3, C is 3 by 2, the 3 and the 3 match, so that one is defined, that one is defined. C times A, I would be doing, what would I do for C times A? It would be a 3 by 2 matrix times a 2 by 3 matrix. Well, that's okay, right? 2's match up, so that one is defined. B times C, I can't do B times C because the 2 doesn't match the 3, so B times C is out. Okay, what about C times B? C times B I can do because C is a 3 by 2 matrix. B is 2 by 2. And so those numbers do match up. Okay, so 4 out of those 6 matrices are defined. Now that we know they're defined, we can work out what they are. So B times A, the size is going to be 2 by 3. Here's how you can kind of think about how to compute this and how to kind of make sure you get the size straight when you do it. If I'm doing B times A, I can put my matrix B on the left, 2, 0, minus 3, 1. I'm going to put A on the right, but I'm going to shift it up. I'm going to put it here. 2, minus 1, 3, 4, minus 3, 5. Okay? And then you can kind of see that things line up for you. Right? 2 rows from the left, 3 columns from the right gives you a 2 by 3 matrix overall. And each of the entries, you can work out what each of the entries should be. If I want to do, let's say, this entry here, this entry corresponds to this row, and it corresponds to this column. So I should do row 1 times column 1. So I do 2 times 2 plus 0 times 4 gives me a 4 that goes in there, right? So basically I multiply this, that gives me a 4, that gives me a 0, and I add them together, and that goes in there, right? And then for the first row in the second column, I do the same sort of thing, but now the 2 matches up with the minus 1, the 0 matches up with the minus 3, so I do 2 times minus 1, 0 times minus 3, and I'm going to get minus 2, and so on. So then if in this entry here, I'm doing this row, this column, so I get 2 times 3 plus 0 times 5, I get a 6. Right? And then again, if I want to know what goes in this spot, I'm in row 2, column 1, and so I do 3 times 2, and I do 1 times 4. So 3 times 2 plus 1 times 4, minus 6 plus 4, I get a minus 2. And so on. So let me fill out the rest. So 3 times minus 1 plus 3 minus 3, I get a 0 here. And then minus 3 times 3, that's a minus 9. 1 times 5 is plus 5. Minus 9 plus 5 gives me minus 4. Okay? Okay. So that's B times A. So B times A is this matrix right here. Okay? And we can do some of the other ones. So I'm not going to do all of them. We don't have room to do all of them, but let's do at least one more. Let's do A times C. So A times C, what's the size going to be? Well, A is 2 by 3, C is 3 by 2, so I look at the numbers on the outside, a 2 and a 2, the size is going to be 2 by 2. Now, I'm not going to compute both of them, but notice that if I did C times A, okay, C times A, the numbers on the outside are 3 and 3. Size 3 by 3, okay? So these two matrices are not even the same size, right? These are different sizes. And what does that tell me? That tells me that regardless of what the entries are, A times C is not going to be the same thing as C times A. They're not even the same size, so there's no hope that these could be the same matrix. So they have to be different. All right, so we'll compute one more just to kind of, again, get a feel for it. Let's do A times C. So let's do A. We'll squeeze that. Actually, let's do C times A. I think that fits in a bit better. 3 minus 4, 1, 0, minus 2, 6. Put A up here. Sorry, I gotta push that down a bit more. Okay. C, 3, minus 4, 1, 0, minus 2, 6. There's C. A, 2, minus 1, 3, 4, minus 3, 5. Okay. And the resulting product, we can see that the resulting product this time has 3 rows and 3 columns. It's a 3 by 3 matrix. And to work out what the entries are, we do this sort of dot product thing, right? So in the first row, I do 3 times 2 plus minus 4 times 4, so 6 minus 16 minus 10. And then I do 3 times minus 1, 4 times minus 3, so 12 minus 3. I get a 9, and so on. 3 times 3, 9, minus 20, negative 11. 1, 0, that 0 there makes it, I just have to multiply, so 1 times 2 plus 0, so I get a 2, minus 1, 3. That one was easy. And then for the last row, minus 2 times 2, I'm down here now, minus 2 times 2, 6 times 4, so 24 minus 4 gives me a 20, and then minus 2 times minus 1, 6 times minus 3, minus 18 plus 2 gives me minus 16, and then finally minus 2 times 3, minus 6, 6 times 5 is 30, 30 subtract 6 gives me a 24. Okay, and I formed that product. Okay, good. One more example, just to kind of play around with these ideas, right? Understanding when is matrix multiplication defined and what can you do with it. I've got 2 matrices there, A and B. I want to find a matrix X so that A times X equals B. The first thing we might ask is that even possible? Can I do A times X and get B? So I'm trying to solve A. So A is going to be 2 by 2. X is, well, we don't know yet. We want to end up with B. B is 2 by 3. Okay? So that 2 and that 2, that matches up. And we know that X has to be, because of the 2 here, we know that X has to be 2 by something. And what is the other thing? Well, the 3 that we have over here, that guy, tells me that I need a 3 there. So X has to be size 2 by 3. Okay? So that means that X looks like, well, X looks like X11, X12, X13, 21, 22, 23. Can I find the entries of X? Well, let's think about what determining the entries of X. What would that entail, figuring out what those numbers are? Well, I would have to first form, I would have to do A times X. So what would I get when I do A times X? I would get first row times the first column, I would get 2x11 minus x21. Okay, what I'm doing here is I'm doing this 2 times that guy minus 1 times that guy. So first row here times the first column here. Then I do this row times this column. So I'm going to get 2x12 minus x13. Then I'm going to get, that's wrong, x22. And then I'm going to do 2x13 minus x23. And then when I get to the next row is a little bit easier, 3, 0. So I'm just going to do, it's going to be 3 times that, and then 0 times that, so I don't worry. Then 3 times this guy, 3 times this guy, so I'm going to get 3x11, 3x12, 3x13, okay, and that has to be equal to minus 1, 0, 3, 0, 2, 4. And now we say, okay, two matrices, they're the same size, so it's possible for them to be equal, and we know that equality means that each entry has the same size. Looking at the second row first is a little bit easier, right? Comparing this entry with this entry tells me that x11 has to be 0. x12, comparing this guy with this guy, we see that x12 has to be equal to 2/3. x13 has to be 4/3. And once we know those values, we can go on and we can figure out what x21, x22, x23 are, because we can take those values, we can plug them in up here and solve the remaining equations. Okay, so part C, I'll let you guys think about that. Can you think about the relative sizes of the matrices? Can you answer the problem, if we're doing x times a instead of a times x? What if we're doing b times x equals a? Do the sizes match up? In which of these scenarios is it even possible to consider the problem? If you can consider the problem, can you figure out what the entries are? Some cases might be easier than others. Okay, so we'll stop here.